Okay, good morning students. So in this video lecture we will discuss about the continuation of a FIR filter design. So the design methods generally the design methods based on specifications of the HD of omega. So one is a design of linear phase FIR filters using window techniques. Second one, the design of linear phase FIR filter using frequency sampling method. So first we will discuss about the design of linear phase FIR filters. Design of linear phase FIR filters using Windows technique. So what do you mean by window? First define window. Because of window, what are the pros and cons? Okay. So normally the function infinite duration, okay, infinite duration will do. So before window function, first we will define the desired frequency response, the specification. So what is a HD of omega? This is the desired frequency response. For the given desired frequency response, this is a desired frequency response. So listen carefully, step by step procedure for designing a FIR filter. First, the desired frequency response, maybe low pass or high pass, band pass, whatever. The desired frequency response for the given desired frequency response HD of omega, you have to determine first step, determine the corresponding. So this is a desired frequency response is given HD of omega. For that you have to determine the HD of omega. Determine the corresponding unit sample response. What do you mean by unit sample response? H of n. Okay, H of n. Further the desired, so desired HD of n. So mathematically the desired frequency response is given by HD of omega is equal to the summation of n equal to 0 to infinity the HD of n, the unit sample response, into e power minus j omega n. Okay. So the next step, second step, is the desired frequency response. Okay. Then the third one, second step, determine the corresponding unit sample response H of n. That is a HD of n. This is HD of n. So now, what is the relationship between HD of omega and HD of n by the Fourier transform ft, Fourier transform. So, what is the relationship between this relationship between the hd of omega desired frequency response and the impulse response hd of n by Fourier transform is hd of omega is equal to hd of omega is equal to okay the summation of, so we return no summation of hd of n e prime minus j omega n. From this we can write, okay, this one not required, so directly we can write. So, the hd of n for it hd of n is equal to 1 by 2 pi integral of minus pi to plus pi hd of omega into e power j omega n d omega. Okay. So, what is the relationship between hd of n? Second step. So, for the given desired frequency response hd of omega, you have to determine the corresponding unit sample response hd of n, which is equal to 1 by, remember that 1 by 2 pi using Fourier transform, 1 by 2 pi integral of minus pi to plus pi hd of omega e power j omega n d omega. So, this hd of n is obtained from this equation, hd of n is obtained from this equation is, what is the duration now? This hd of n you can obtain from this equation, or what is the duration now? 0 to infinity. So, this is infinite in duration and it must be truncated, this infinite duration. Note down, this is a infinite duration. Infinite duration must be truncated at some point, must be truncated at some point, truncated at some point. So, what is the some point? At, for example, say at n is equal to m minus 1, at n is equal to m minus 1, n is equal to m minus 1, to yield FIR and to yield an FIR filter of length m, okay, of length m. So, now, so this truncation, you are truncating this infinite duration into finite duration is called window techniques. Now, what do you mean by window? What do you mean by window? Window technique, truncating. Window means truncating. So, truncating an infinitely long signal, to a finite length signal. So, by using window technique, we are truncating the infinitely long signal 0 to infinity to a finite length signal. That means truncation of HD, okay, truncation of HD of n to a length m minus 1, to a length m minus 1. So, the truncation of HD of n to length m minus 1 is equivalent to, is mathematically, which is equivalent to multiplying HD of n by a window, by a, you can say is a for example, rectangular window. Window may be any type of window, different types you can classify into rectangular window, hanging window, Blackman window. Rectangular window or other windows techniques or other window techniques. Okay. So other window techniques means the other windows are hanging window, Blackman window. Some windows Blackman window. I specify some of the window techniques other than rectangular window. So the truncation can be done by multiplying the HD of n by one of the rectangular window techniques. Okay. What do you mean by window techniques? So we are truncating. Okay, we are truncating. For example, if the sequence is, so this is a sequence. See, this is a sequence. Periodic sequence. This is a periodic sequence. Okay. This is a periodic sequence. So what is a window sequence here? This is a window sequence, for example. This is a window sequence. Window sequence. If the window width is an integral multiple of periods of all the frequency components of a discrete signal, then the window sequence is identical to the original discrete signal, and the DFT will produce a single spectral coefficient corresponding to each frequency component. So, but because of the window actually, because of this window technique, we are truncating the infinite sequence into finite sequence. There will be a discontinuity. There will be discontinuities. Okay. So what do you mean by window? Actually, because there is a discontinuities, window causing. So this window, because of this window, it causes discontinuities. It causes causing discontinuities. Okay. Discontinuities means what? It's a spectral leakage. Discontinuities means spectral leakage. Window because of this spectral leakage. So spectral leakage. So windowing means, what do you mean by window? We are truncating the infinite sequence into finite length signal. Okay, finite length sequence. Because if the window sequence differs from the original discrete signal with the discontinuities, okay, which occurs at the boundaries of the window. Boundaries of the window will result in the DFT will produce non-zero spectral coefficients. Non-zero spectral coefficients at all frequencies This phenomena is known as spectral leakage. What do you mean by window technique? We are truncating the infinite sequence into finite sequence, which causes discontinuities will be occurred at the boundaries, which results non-zero spectral coefficients at all frequencies. So, this phenomenon known as spectral leakage. So, how you can get the window sequence mathematically? So, mathematically you can multiply this sequence HD of n with one of the window techniques. How you can truncate the sequence length HD of n to m minus 1, which is equivalent to multiplying HD of n by any one of the rectangular window. So, window technique means what you are doing, you can write x of n window techniques, which is equal to multiplying by the window function Wn, this multiply. So, normally the rectangular window function used to produce the window sequence. So, the window sequence x of n, you can produce the product of generated by the multiplying the signal x of n and the window function w of n. So, normally the multiplication of window function w of n with the hd of n, with this hd of n plus hd of n is equivalent to the convolution of hd of omega with w of omega in the frequency of domain representation. Clear? So, the window function now you can define for different window function. So, the rectangular window function, here I will write rectangular window function. So, w of n, you can define the w of n is equal to 1 for n is greater than or equal to 0, less than or equal to m minus 1, 0 otherwise. So, now the unit sample response, you can write the unit sample response. The unit sample response hd of n, the unit sample response of now the FIR filter becomes h of n, which is equal to the unit sample response of FIR filter h of n becomes you multiply hd of n into the window function w of n. So, although the rectangular function is the simplest one to implement, it is very simple to use because w of n is equal to 1 for 0 to m minus 1, 0 otherwise. Even though it is very simple to implement, it is very worst to use in spectrum analysis. If you consider spectrum analysis, if you use the rectangular window, it is the worst to use in spectrum analysis because if you use a rectangular window, the disadvantage is rectangular window if you use, the spectrum analysis will be worst because of large discontinuities will be there, large discontinuities. discontinuities will be there. Okay. So that more spectral leakage will be there because of this more spectral leakage. So what is the disadvantage of rectangular window technique? One is large discontinuity because of this more spectral leakage. So first step, if you see the first step, what is the first step? For the given desired frequency response HD of omega, you have to determine the impulse response HD of n, which is equal to 1 by 2 pi minus pi to plus pi HD of omega e power j omega n. Then okay, you go for the window technique. What do you mean window technique? The infinite duration, truncation of infinite duration into finite duration at m equal to m minus 1. So it yields FIR filter with the length m. So window means truncating an infinite into finite length. How you can truncate infinite into finite length? Multiplying the HD of n by window function. The window function may be rectangular window or other window technique. So window means truncation. Because of this truncation, the spectral leakage will be more, and in rectangular window function, the discontinuity will be more and more spectral leakage. Okay. So the unit sample response of the FIR filter can be written as H of n is equal to HD of n into W of n. This is the third step actually. Then the fourth step will be, okay, fourth step will be, you have to, the first, so you can write down the steps first, otherwise I will write down here. Fourth step will be realization. Realization, how do you, the hardware realization from the system function, added multiplied unit element, you have to take, that is the realization for that one, from H of n to convert H of z. This is a H of z. H of z. System function will be in the digital form. Digital. So this is the digital filter. Realization, take z transform of H of n to z transform. You are taking H of n, then z transform H of z. It is a system function of digital filter. Then realization, hardware realization. Hardware realization. So now you can the various steps, we can list out the various steps in designing FIR filters. Okay, the first step, choose an ideal, or you can say is a desired frequency response. Frequency response HD of omega. Second step, take inverse Fourier transform, inverse Fourier transform, inverse Fourier transform, inverse Fourier transform. Okay, inverse Fourier transform of HD of omega to get HD of n. Third step, convert infinite duration infinite duration hd of n to a finite duration finite duration h of n. Next step, take Z transform. Take Z transform of h of n to get h of z. This is a system function of digital filter. Next step, realization. Realize the filter. So how to realize the filters? Already we have discussed the realization of filters. How to realize the filters? What are the three components, important components of filters? For example, here h of z is equal to, for a FIR filter, okay, x of n divided by the unit delay z inverse, you will get x of n minus 1. Then if you go for z another one more unit delay, then you will get x of n minus 2. Okay. Then z inverse again x of n minus 3. Then finally another z minus 1. So we will get, so here what are the coefficients? The coefficients are h of 0, first one, h of 1, h of 1, both will be added. Then here h of 2 which will be added. H of 2 h of m minus 2, this will be h of m minus 1, z minus 1, h of this is m minus 2, which will be y of n. So that direct form realization of FIR filter. This is a direct realization. Direct form realization. So that is the equation, or the equation here, h of z is equal to, so this equation belongs to, this realization belongs to h of z is equal to the summation of k equal to 0 to m minus 1 h of k into h of k into z power minus k, k equal to 0 to minus 1. So h of 0. So this is a bk coefficients. Actually in FIR it will be a bk coefficients. Okay, in FIR filter you can write h of z is equal to, okay, normally we used to write h of z is equal to summation of k equal to 0 to m bk into z minus k, impulse response coefficients, so that we have studied already. So this is the various steps to design a FIR filters. First, you choose the ideal desired frequency response HD of omega, take inverse Fourier transform HD of omega to get HD of n, and convert infinite duration to finite duration. So, how do you convert infinite duration to finite duration there? Infinite duration into finite duration will be, so mathematically, so this will be HD of omega, they take inverse Fourier transform. So, that is equal to HD of n is equal to, that is the equation 1 by 2 pi minus pi 2 plus pi HD of minus pi 2 plus pi HD of omega into e power j omega and d omega. So, first step is choose the desired frequency response HD of omega. Second step is take inverse Fourier transform of this to get HD of n. Third one, you multiply h of n, convert infinite duration into finite duration to get finite duration, which is equal to h of n is equal to HD of n into the, by multiplying the window function w of n. Okay. Then using h of n obtain, using h of n you can obtain the magnitude response h of omega for various values of omega, for various values of omega in the range omega 0 to pi, the range of 0 to pi, and sketch the graph between the magnitude response h of omega and omega, which is the frequency response. Okay. So, here you convert the infinite duration into finite duration by using, I told you here with one more points we can complete this session before starting to solve the problems using window technique, because as I said, the rectangular window has more spectral leakage, because of spectral leakage the phenomena is called you can observe there is a sudden shoot up in the pass band, there is a sudden overshoot in the pass band, that is called Gibbs phenomena. Okay. So, among various types of window technique, so that we can some of the cosine based window can be formed. So, here one more term I will explain. So, the Gibbs phenomena, what do you mean by Gibbs? Gibbs phenomenon. For that you know the frequency characteristics. So, there will be ripples in the pass band. Okay, this is the ideal characteristics. Ideal characteristics will be, this is the ideal one, but there will be ripples in the pass band with the tolerable 1 plus or minus del 1. Okay, this is the ideal one, but you will not get the ideal one, as I said. The ripples, okay, because of discontinuities, because of spectral leakage, there will be sudden overshoot. This is called overshoot. Okay, sudden overshoot. There is a ripples in the stop band. This is del 2. This is a del 1. Okay, this is 1. This is 1. This is a plus or minus del 1. So, response. So, this is your ideal. This is your ideal curve. This is your ideal curve. But these are the ripples. Okay. The impulse response. So, the impulse response sequence, the h of n, the impulse response sequence is modified by the window function. Okay. Modify the window function is included to minimize the oscillations, to minimize the oscillations. So, these are the oscillations. There is you can observe as ripples. You can observe as ripples and the overshoot in the frequency characteristics or magnitude characteristics, which is known as Gibbs phenomena. Okay. So, which is caused by how it is happened because of truncation, because of truncating the infinite impulse response of the ideal filter to a finite impulse response of sequence m values. Okay. So, the Gibbs phenomena caused by, which is caused by truncating the infinite impulse response into finite impulse response sequence of m values. So, the truncation of Fourier series, so the truncation of Fourier series introduces the truncation introduces ripples in the frequency response characteristics h of omega, okay, due to the discontinuity, and this oscillatory behavior is called Gibbs phenomena. This oscillatory behavior is called Gibbs phenomena. Okay. So, with this you can conclude this session. So, next session we will solve the problems using so I one more point. So, before closing the session, one more point. So, as I said, because in the window technique, yes, in the window technique there, in the window technique, rectangular window we have discussed, and in the rectangular window more discontinuities, more spectral leakage is there. So, that for we are using some cosine based windows, or you can say some tapered windows, various types of instead of rectangular, among various types of tapered windows, some cosine based windows are formed. The cosine based windows are Hamming window, Hanning window, Blackman window. Okay. So, that mathematical equations for different cosine based windows we will discuss in the next session. So, the discontinuity and the oscillating behavior, the overshoot, all will be spectral leakage will be more in the rectangular window compared to cosine based window. So, various types of tapered windows, that is a cosine based windows can be used to reduce the sudden overshoot in the pass band. That we will discuss in the next class. Thank you.